Welcome to part 2 of our machine learning module. Today we cover classification, neural networks, and how to structure your computational mini-projects. Our learning outcomes for this lecture include distinguishing classification from regression, training a simple classifier, interpreting a confusion matrix, and learning how to use AI responsibly in your coding workflow. Let us briefly recap part 1. In supervised learning, we use input features to predict target values. While part 1 focused on regression for continuous numbers, today we focus on classification, where the target is a discrete category. We begin by importing the necessary Python tools. We are using NumPy, Pandas, Matplotlibs, and several modules from scikit-learn for building and evaluating our models. We complete our imports by bringing in the specific metrics we will use, such as accuracy score and confusion matrix, and set our random state for reproducibility. The output confirms that all our required libraries have been imported successfully and we are ready to proceed. Classification is a form of supervised learning that predicts a class label. For example, classifying a materials phase or identifying a handwritten digit. The workflow is very similar to regression. We prepare the data, split it, train a model, and evaluate its predictions. Let us look at a first example using simulated motion types. We will use simple features like mean speed, speed variation, and direction changes to classify motion as uniform, accelerated, or oscillatory. We start by generating this synthetic dataset. We create random distributions for uniform and accelerated motion, assigning distinct numerical features to each class. We continue the data generation by defining the parameters for oscillatory motion. Then, we concatenate these into a single pandas data frame and map the numerical targets to descriptive labels. To check our synthetic dataset, we sample a few rows from the data frame to ensure the features and labels are correctly aligned. The output table shows our sampled data. You can see the different features like mean speed and standard deviation alongside their corresponding motion type and descriptive label. Visualizing the data is always a good practice. Here, we write a short loop to create a scatter plot of speed standard deviation versus direction changes for each motion class. The resulting plot shows how our three classes are distributed. We can clearly see the clusters representing uniform, accelerated, and oscillatory motion, though there is some overlap that will challenge our classifier. Now we will train a decision tree classifier. After isolating our features and target, we split the data into training and test sets and initialize our classifier with a maximum depth of 2 to prevent overfitting. We finalize the training step by fitting the model to our training data, predicting the labels for our test set, and calculating the overall accuracy score. The output shows an impressive test accuracy of roughly 98%. However, a single accuracy metric does not tell the whole story. To better understand our model's performance, we use a confusion matrix. This matrix compares the true labels in our test set against the labels our model predicted. Looking at the plotted confusion matrix, the diagonal shows correct predictions. We can immediately spot that one instance of oscillatory motion was misclassified as accelerated motion. Beyond the confusion matrix, we can calculate a detailed classification report. This code sets up the report to show precision, recall, and F1 scores for each individual class. The printed output confirms our overall test accuracy again, providing a quick check before we examine the detailed metrics. The classification report table provides a granular breakdown. Notice how the recall for oscillatory motion is slightly lower, reflecting the misclassification we saw in the confusion matrix. A good classification result must be interpreted scientifically. In our example, the model succeeds because the physical features generally separate the motion classes well, but the slight overlap causes realistic misclassifications. Next, we move to a neural network style classification. We will use a simple multi-layer perceptron on the built-in scikit-learn digits dataset, where each image is an 8x8 grid of pixels. The output confirms our dataset shapes. We have over 1,700 images, each flattened into 64 pixel features, along with their corresponding target digit labels. Before training, let us visualize the data. This code sets up a grid of subplots to display the first few images from the digits dataset. The plot shows the low-resolution, handwritten digits we are working with. Our model will learn to recognize the pixel patterns associated with each number from 0 to 9. Because pixel values have numerical scales, it is best to standardize them. We split our dataset and set up a pipeline that scales the data before feeding it into our neural network classifier. We configure the multi-layer perceptron with a single hidden layer of 32 neurons, then fit the pipeline to our training data and calculate the test accuracy. The test accuracy is 98%. Our simple neural network has performed very well at recognizing these handwritten digits. Just as before, we want to see exactly where the model made errors. We use the confusion matrix function again to evaluate the predictions across all 10-digit classes. The resulting confusion matrix is much larger. Most predictions fall neatly on the diagonal, but we can spot a few off-diagonal numbers indicating specific digit confusions, like mixing up an 8 and a 1. Let us write some code to extract and display the specific images that were misclassified. This helps us see if the model's mistakes make sense visually. This final piece of code just handles the edge case where no images are misclassified, ensuring our plotting logic does not fail. The output tells us that exactly 9 images in our test split were misclassified by the neural network. Looking at the misclassified digits, we can often see why the model struggled. For instance, a messy 8 might look very much like a 1 or a 9, even to a human eye. Interpreting neural networks requires caution. The model does not understand digits, it only maps pixel patterns. High accuracy describes performance on this specific dataset, but it does not guarantee the model has learned a universal scientific truth. Now let us discuss responsible AI-assisted coding, sometimes called vibe coding, in machine learning projects. AI tools are great for debugging or outlining, but they must never replace your own understanding of the workflow and data. A responsible workflow means stating your problem clearly, sketching the logic before writing code, and explaining every step yourself. If you use AI to generate a code skeleton, you must still run, verify, and understand each block. As you prepare for your mini project, make sure your report covers the full workflow. You should clearly state the problem, describe your dataset, identify features, and justify your pre-processing steps and algorithm choices. Your project should use suitable introductory algorithms like logistic regression, decision trees, or k-means clustering. Remember to tailor your choice to whether you are doing regression or classification. Be aware of common mistakes. Do not confuse features and targets. Always use a train-test split, and never trust a model blindly without inspecting the data and metrics. To build your skills, try these guided practice tasks. Experiment with the decision tree depth, modify the hidden layers in the neural network, and practice writing responsible AI prompts. To summarize, classification predicts categorical labels and requires careful evaluation using tools like confusion matrices. Always interpret your results scientifically and maintain a rigorous, verified workflow when building your mini projects.